Hello. 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 Am I audible?
Yes, sir.
Yeah. Okay. We'll start the today's session. So I hope you have gone through the lecture videos. So this session is about solving the problems, some of the standard problems not related to your assignment or your ordinary problems. So this time we are going to solve some interesting problems on the topic of evaporation and evapotranspiration. So today we'll be solving the problems on the estimation of the evaporation rate. So we have different methods. First is the energy balance method, then second method is aerodynamic method, and third method is the combined energy balance and aerodynamic method. Then later on we'll be seeing the estimation of pan evaporation and the lake evaporation. And third kind of problem is estimation of the reference crop evapotranspiration using the Penman-Monteith equation. And the last problem will be on crop evapotranspiration and crop coefficient. So we'll move on to the question number 1. So first is related to the calculation of evaporation rate. So the question is the 2-hourly data from a weather station that is placed at 2 meter above the ground level near the surface of the lake is given in the table. So if you see this table, we have hours. So the weather data has been measured for different time intervals throughout the day. SW in, SW out, which is the short wave radiation. Short wave radiation is nothing but the incoming solar radiation, and LW is the long wave radiation which is emitted from the earth. That is LW in and LW out. And we have the air temperature, then TW is the water temperature, RH is relative humidity, and V is the wind velocity, and this wind velocity is measured at 2 meters above the ground level. In addition to that, so the table consists of incoming and outgoing short wave and long wave radiation. We have air and water temperature in degrees centigrade. Then we have relative humidity, wind speed. So in addition to all these data, atmospheric pressure has been given as 101.3 kilopascals, and you have the different coefficients which is used in the energy balance method and the aerodynamic method. KV is given as 2.7 into 10 to the power of 8 per kilopascal. Then you have KH is given as 4.4 joule per degree centigrade per meter cube. And you have the constant to determine the psychrometric constant, that is 1005 joule per kg per Kelvin, and the psychrometric constant is also given 67.38 pascals per degree centigrade. So some additional data is given as CA. And now we need to estimate what is the evaporation rate from the lake using the energy balance method. So in energy balance method, we will see the equation. So first condition is assuming no ground heat flux. Then second question is energy balance method accounting for the sensible heat and neglecting the ground heat flux. And the aerodynamic method considering the roughness height at the ground level as 0.03 centimeter. And the last one is combined aerodynamic and energy balance method. So we can assume any other data that is required to solve this problem. So first, I'll write down the basic energy balance equation. So did you understand the question? Hello?
Yes.
Did you understand the question, like what is given and what needs to be found?
Yes, sir. Yes, sir. Very well.
Yeah. So now I am writing the basic energy balance equation. So your evaporation rate from the energy balance equation is given as net radiation minus your sensible heat flux minus the ground heat flux divided by latent heat of vaporization into density of water. So this is the basic equation, and in this usually while solving problems in question it will be given to neglect the sensible heat as well as the ground heat flux. In this determination of the ground heat flux is a little bit tricky part, so usually we'll be neglecting for our calculations, but sensible heat can be calculated. So we'll see how to take into account the sensible heat in the part B of the problem. So right now the part A of the problem, we are neglecting the sensible heat and the ground heat flux. So your evaporation rate is simply net radiation divided by latent heat of vaporization into density of water. Now how to determine this net radiation? So net radiation is a function of short wave radiation and the long wave radiation. So this is the data that has been given in the question. So we will write this as short wave radiation incoming minus short wave radiation that is going minus long wave radiation that is outgoing minus long wave radiation that is incoming. So this term is your SWN and this term is your LWN. Now if you see the table, so we'll be making use of SW in, SW out, LW in, LW out for different durations. So we'll calculate. So I'm going to calculate this particular table. So here for different duration, SW in, SW out, LW in, LW out, and your net radiation, this is in watt per meter square. So first is your short wave radiation. These are all given in the question. So we'll be applying this equation 1 to determine the net radiation. So if we do that, so we'll be getting minus 60, minus 40, 85, 330, 75, minus 55 and minus 55. So can you tell me why we are getting some negative net radiation? So what could be the reason?
outflow minus inflow.
Yeah, but you can see with respect to the time. So if we consider 0, let's say that they are they are measuring the shortwave radiation early morning, like before sunrise. So when there is no sun, there will not be any incoming radiation.
Okay, okay, okay.
But your objects on Earth, they will be emitting the long wave radiation because of the heat that is stored from the previous day, right?
Yes, yes, yes.
So we are getting negative radiation. So when you get a negative radiation, you will get negative evaporation, which means there is no evaporation taking place. So while calculating, we'll see that we'll get negative evaporation rate, and we should be knowing why we are getting negative. So, and as the time increases, you can see the net radiation increases, and again it drops during the night time. So that is what we can interpret from this particular table. So now we have calculated the net radiation.
Okay.
Next, we need to determine the latent heat of vaporization. So your LV term, your denominator. So for that, we have a empirical equation. So LV is given by this empirical equation, 2.501 into 10 to the power of 6 minus 2370 into your temperature of the air. So here TA is in degree centigrade. So for different time of the day, we have different air temperature, and we'll be calculating the latent heat of vaporization for that particular time period. And we also have the density of water. So density of water also changes with time. So we can refer to some standard tables, and then we can interpolate for the corresponding temperature at which we need the density of water. So we have the air temperature in degree centigrade as 30, 28, 30, 35, 38, 33 and 32. So I have already calculated the latent heat of vaporization. Its unit is joule per kg. So it is 2.4299 into 10 to the power of 6. And I have also calculated the density of water corresponding to different temperatures. So this is 995.6, 996.26. So it comes like this. So we have now calculated your net radiation, your latent heat of vaporization and density. So next we can directly compute the evaporation rate. So I am doing a sample calculation for one of the table values. So let's say at 0 hours we have evaporation rate is equal to, so from the table if we see, your net radiation is minus 60. Minus 60 divided by your latent heat of vaporization is 2.4299 into your density is 995.6. So this will give you the evaporation rate in meter per second, but we need it in terms of per day. So I am multiplying by 1000 to convert to and again multiplying by 86400. This is nothing but 24 into 60 into 60. So I'm converting it into per day. So I'll get a value of minus 2.143 per day. It just signifies that there is no evaporation taking place, but there is a condition. Suppose at 0 hours, if the temperature of the air is equal to your dew point temperature, then what will happen? If the temperature of the air is equal to dew point temperature,
temperature into
temperature of the air at 0 hours, let's say early morning, if the air temperature is equal to your dew point temperature, then what will happen?
then it's value in the plus maybe 0.14.
No. So if the temperature is equal to dew point temperature, then what happens is your saturation vapor pressure. So if you calculate the saturation vapor pressure,
Okay.
your vapor pressure will be equal to your saturation vapor pressure. So both will be equal, which means your relative humidity is equal to 100%.
Okay.
So if the relative humidity is 100%, then there is a chance that condensation might happen.
Yeah, condensation. Yeah.
So early morning you can see on the surface of the leaf you can see some water droplets, right?
Yes.
So that is because of this only. So that much will be your condensation that is happening. So we'll calculate for another time, maybe some peak time. Let's say you are getting the peak at 12 hours, I think. At 12 hours, E is equal to 330 is the radiation. So I'm writing the conversion unit divided by 2.4181 into 10 power 6 into density is 994.
Okay.
Different temperature is changing.
Yes. Yeah.
E is equal to 11, that comes out to be 11.86 So this is how you calculate the evaporation using the energy balance method without considering your sensible heat and the ground heat flux. So now part B of the question, energy balance with sensible heat and no ground heat flux. So sensible heat can be calculated as Hs is equal to Kh into velocity of the wind into temperature of the water minus temperature of the air. This is the expression that has been derived. So using this expression we can compute how much is the sensible heat. So again this also varies for different temperatures. So for this we need temperature of the water, we need temperature of air, and we need wind velocity also. And Kh in the question is given as 4.4 joule per degree centigrade per meter cube. So we'll compute the Hs. So this is 33, 32, 33, 34, 35, 4 and 33. Air temperature is given as 30, 28, 30, 35, 38, 33, 32. So your wind velocity is also given in question. 3.5, 3.1, 2.6, 1.6, 2.1, 2.4 and 3.1. So we can, it's just direct multiplication. Units, there is no change in the unit. It's all standard units only. So your temperature will be in degree centigrade. This will be in meters per second and constant in terms of the given units. So you will get your sensible heat as 46.2, 54.56, 34.32. You are getting some negative term. So if you see now, you are getting a negative sensible heat flux because your water temperature is less than your air temperature. So this will be somewhere in the peak sunlight, that is in the afternoon.
Okay.
10.56 and 13.64. So if you see the energy balance equation, the basic equation, so you have net radiation minus sensible heat. So sensible heat is actually reducing the effect of the evaporation rate, because some amount of heat is going out of the system. So now we have estimated the sensible heat. Now our evaporation rate equation will be net radiation minus sensible heat divided by LV into rho W. Same as the previous, we can calculate at 0 hours. Your evaporation rate is equal to, so first is minus 60 and minus 46.2 divided by 2.4299 into 10 to the power of 6 into 995.6. So again this will be in terms of meter per second. I am converting to
1000
into 1000 into 86400. This will be equal to minus 3.792 mm per day. So we'll compute for another time where the peak is coming. So we'll take the same 12 hours. So it is 330 minus of minus 7.04 divided by 2.4181 into 10 to the power of 6 into 994.06 into 1000 into 86400. So we will get 12.115 mm per day. So this is your evaporation rate by the energy balance method, without considering the ground heat flux and considering the sensible heat flux. So you can maybe plot this, maybe we can plot something like this and we can see the difference that is occurring. So I am leaving that up to you. So here you can plot the time and here you can plot the evaporation rate. So this will go something like this, and with your sensible heat flux, So you can plot and check how it is varying.
Yes, sir.
So this will
And
be.
it vary in evaporation with rise.
So this is not temperature. This is time in hours.
Yes, okay.
So throughout the day, how your evaporation is varying by using different methods. So we can plot and see, and we can interpret some of the results. So now coming to the part C of the question. Estimate the evapotranspiration by using the aerodynamic method. So before that, I will say the assumption that we make in the energy balance method. This is one of the important assumptions. So here the assumption that we make is the vapor transport is not a limiting factor. So for the evaporation to occur, we need some energy and we need vapor transport. So here we are assuming that the vapor transport is not limiting. That means we are considering there is no issue in conversion of the water to the vapor and for the vapor to get transport. So everything is happening within a closed system, and this is the assumption that we make in the energy balance method. So similarly in aerodynamic method, so we can use the energy balance method when the vapor transport is not a limiting factor. So I cannot say this as assumption. So use the energy balance method when the vapor transport is not a limiting factor. So similarly, we can use aerodynamic method when the energy is not a limiting factor. So here because in aerodynamic method the way we derive the equation is based on your momentum equation, and your continuity equation. Here we use continuity equation and energy equation. Okay, now we can see the expression that was derived for the aerodynamic method. So the entire expression is EA is equal to 0.622 into K square rho A into ES minus EA whole divided by density of water into pressure into U2 is velocity measured at 2 meter above the ground level, then into natural logarithm of Z2 by Z1. This is nothing but the elevation. So here K is the Kármán constant. This is from your boundary layer theory. That is equal to 0.41. Then you have Z1 is the roughness height at ground level. Z2 So now in this equation we need to compute saturation vapor pressure, then your vapor pressure, then we need to compute the density of air. So they are also varying with your temperature parameters. So again I am writing the air temperature. This is 30, 28, 30, 35, 38, 33. So this is in degrees centigrade. Now we need temperature of the air in Kelvin, because your density of air is equal to pressure by Ra into T, and this T is in Kelvin. And Ra is the gas constant, that is 287 joule per kg per Kelvin. Let me write. Joule per kg per Kelvin. Then we need to compute saturation vapor pressure. Relative humidity is given in the question. Then once we get these two, we can compute the vapor pressure of the air. So these are the terms that we want. Now this is 273 plus temperature in degree centigrade. So we can compute directly. This is 303, 301, 308, 311, so this is again 303, 308, 311, 306 and 305. So the pressure is given as 101.3 kilopascals. So we can directly substitute and we can compute the air density. 1.164. This unit is in kg per meter cube. 1.173, 1.164, then 1.146, 1.135, 1.153, this is 1.157. So next we can compute the saturation vapor pressure. So we have the standard expression 0.611 into exponential of 17.27 plus air temperature 237.3. Sorry, this is multiplication into air temperature. So here denominator it is additive. So here this temperature of the air is in degree centigrade and you will get the saturation vapor pressure in kilopascals. So we can compute for each of the air temperature. So this unit is in kilopascals. I have 4.244, 3.781, again 4.244, 5.624, 6.627, 5.032, 4.756. So relative humidity is given in the question. So it is given in percentage, but we will convert it into fraction. So 0.90, 0.85, this is 0.75, 0.60, 0.70, 0.85, again last also 0.85. So EA can be calculated as, so if we know the relative humidity definition, relative humidity is equal to vapor pressure of the air divided by the saturation vapor pressure. So from this we can get vapor pressure of the air is equal to relative humidity into saturation vapor pressure. So again that will be in kilopascals. So if we compute, this is 3.819, 3.214, 3.819, 3.374, 4.639, 4.277, 4.043. Now if you see, we have got all the things which we want for our calculation. So now we can proceed with our calculation. So estimation of evaporation rate by aerodynamic method is equal to, so first is 0.622 is the constant into your Karman's constant is 0.41 square divided by 101.3 is your pressure, that is in pascals, multiplied by, so again this is varying with respect to the parameters for each time step. So I'll compute for at T is equal to 12 hours, which is the maximum evapotranspiration is occurring at that particular time, into 1 divided by natural logarithm of Z1 is 2 meters, where we are measuring the air temperature and all the other parameters, and Z1 is the roughness height. So in question it is given as Z1 is equal to 0.03 centimeters. So we'll be substituting it in meters, 0.03 into 10 to the power of minus 2 meters. And this term we need to square it. And we have the density of air in the numerator, 1.135 multiplied by 4.2 at T is equal to 12 hour, your saturation vapor pressure is 5.624 minus air vapor pressure of the air is 3.374. So again this into 10 to the power of 3. So I am converting the kilopascals into pascals. So So I will remove this. Multiplied by your wind velocity, which is u2. u2 is 2.1 meter per second. So again this will give in terms of meter per second. We need to convert it into mm per day into 1000 into 86400. So I have just written the expression in a way that is convenient for calculation. So this EA will work out to 5.931 mm per day. So similarly we can calculate for all the other time step. So I will just write the values directly for all the other time step. 0, 4, 8, 12, 16, 20 and 24. This is hours, and EA is estimated. So that comes out to be 1.908, then 2.273, 1.419, 4.558. So this is T is equal to 16 hour, it is maximum. I'm just making a change here. 5.931, 20th hour 2.306, and this is 2.822. So I made the sample calculation for the 16th hour, it's not for the 12th hour. Okay. So this is how you estimate the evaporation rate by using the aerodynamic method. So again you can plot this also in terms of your here you can have time, and here you can have your EA, and you can compare this with the previous graph also. You can see the difference between the energy balance method as well as your aerodynamic method. So what is the difference in the evaporation values? Now last part of this question is the estimation by using the combined method. So I just told two assumptions or the two conditions under which we derive both this equation. So the first condition is vapor transport is not limiting. Vapor transport not limiting for energy balance, and in aerodynamic method energy is not limiting. But in reality we don't get infinite amount of energy all the time, and similarly vapor transport also does not happen all the time. So both are limiting factors. So in that case only they have derived a combined method, which is the evapotranspiration by using the both aerodynamic as well as your energy balance method. So we are moving from some assumptions to the reality. So here both are not limiting. Combined energy balance and so in reality both are limiting factors. So here both vapor transport and energy are limiting. So they have derived a kind of like empirical equation by taking the weightage of both the energy balance as well as the aerodynamic method. So the expression for the combined method is E is equal to delta by delta plus gamma. This is the weighting factor multiplied by evaporation rate from the energy balance method plus gamma by gamma plus delta into your evaporation rate from your aerodynamic method. So this equation is known as Thornton-Helmholtz equation. Here delta is the vapor pressure gradient. This was taught in the precipitation module. And gamma is a psychrometric constant. So gamma has an expression, but in this question gamma is directly given. So gamma is equal to 67.38 pascals per degree centigrade. And we will calculate the vapor pressure gradient because vapor pressure gradient is given as 4098 into saturation vapor pressure divided by 237.3 plus TA the whole square. This is nothing but how it is derived is we have the expression for your saturation vapor pressure. We are just differentiating with respect to the temperature. That's it. So if you do that, you will get this. You will end up in this expression. So the unit of this is also Pascal per degree centigrade. So here the air temperature is again varying throughout. So we will calculate the gradient for each temperature throughout the day. So your temperature is in degree centigrade 30, 28, 30, 35, 38, 33 and 32. Then your delta is the vapor pressure gradient. This is in Pascal per degree centigrade. So I have already calculated 243.42, 220.14, 243.42, 310.83, 358.32, 282.24, 268.75. So now we just have to substitute in this equation with respect to the corresponding evaporation rate from the energy balance method and your aerodynamic method. So these numerator and denominator has the same unit, so it's just a number, and EA will be in mm per day itself, and your evaporation rate, this will also be in mm per day. So I'll do a sample calculation for 16th hour. Let me do for 12th hour itself, because we are doing for 12th hour mostly. So your evaporation is equal to, evaporation rate is equal to 310.83 divided by 310.83 plus gamma is 67.38 into evaporation from the energy balance method, that works out to be 11.86 mm plus 67.38 divided by 67.38 plus 310.83, and the corresponding evaporation rate from aerodynamic method is 4.558. So if you compute, this will give you 10.559 mm per day. So this is how you estimate the evaporation rate by using the combined method. So this marks the end of the first question. So second question, we will see about estimation of the pan evaporation and lake evaporation. So your second question is something like this. So here we need to compute the daily evaporation that is happening from a class A pan if the daily rainfall and the amount of water added to bring the water level in the pan to the fixed point are given as follows. So for every day you have some rainfall, and we are also adding some water to the evaporation pan. So I'll come, if you see we have some negative values here, I will just let you know what is that. So if you see the evaporation pan, it is something like this. It's circular in shape, and you will have a fixed level of water. Let's say this is the fixed level of your water. So you know this particular elevation. So that is the standard point. So your evaporation is happening, and sometimes you might get precipitation also. So we are assuming that this evaporation pan is well protected from the hindrance due to the birds, or there is no other source of water to it, and all these other assumptions. So we are just considering there is only evaporation that is happening from the pan, and you are getting the precipitation into the pan. So now what happens as evaporation takes place? So I'll mark the evaporation with the red color because it's going outside. As evaporation happens, so let's say this is the initial level of water. So as evaporation happens, your level comes down. So that amount of depth is what is given. That amount of depth only we need to calculate. So this one we need to calculate. Now we have some precipitation also. Some days precipitation might be more than your evaporation. That means it will go above your fixed level. So that time what you will do, we are measuring all our measurements with respect to this green line only. So we will remove some water. We won't add water, we will remove some water. So in this case we will be adding water. So adding water is positive quantity, and removing water is negative quantity. So now if you see the table, so first day the rainfall is 10 mm, and amount of water added is -3. So it is possible that that particular day you might not have that much of evaporation, So the water level went above the fixed level and you are removing some water. So that is what is given in this table. So the negative indicates that water has been removed from the pan. Now we need to compute what is the daily evaporation and the total evaporation from the pan at the end of 7 days. And there is if the surface area of the lake is 750 hectares in the vicinity of the pan, so the pan is located nearby some lake, and we need to compute what is the evaporation from lake at the end of the 7th day, and we also need to find what is the volume of water that is lost by evaporation from the lake, and we can assume the pan coefficient as 0.8. So you understood the question. The data represented in the table. Hello.
Yes, sir. Yes, sir. I understand.
Yeah. Okay. So now we need to compute the daily pan evaporation. And total evaporation. So your daily evaporation is given by amount of water required to bring the water level to fixed elevation plus water contributed by rainfall. So this is day 1, 2, 3, 5, 6 and 7. So you just have to add these two quantities. So if you add these two, this is the amount of water that is added to bring the water to the fixed stage. So that day the evaporation is less and the precipitation happens, so water has accumulated. So the summation of this will give you the amount of water that is actually evaporated. Correct? Yes. So your net pan evaporation. So this is in mm. Sum of your precipitation plus the other one. So this will be 7, 9, 8, 8, 6, 8 and 3. So we have just computed this is the daily evaporation. Now we need to compute the total evaporation. It's just summation of all the things. 7 plus 9 plus 8 plus 8 plus 6 plus 8 plus 3. So this is equal to 49 ml. So this is your evaporation from the pan. Now part 2 of the question. So nearby there is some lake, we need to estimate the evaporation from lake. So evaporation from lake is equal to Cp into evaporation from the pan. So Cp is pan coefficient. So do you know the reason why we are multiplying it with pan coefficient? What is the reason? Any idea? Okay, we are multiplying because your pan is a closed cylinder and it is made up of metal, and it has some height h.
Yes.
So this pan total height is some h. If you have that much height, let's say, and so this is the, let's say if this is the pan, first of all it is above the ground level, so it will be placed above the ground level only. Let's say your lake level is this. So you have the pan here. So first it is above the ground level, that is one factor. Then
Yes.
the amount of incoming energy on both are different because it has metal, and you might have some shade during the different time of the day. The placement will be such that there is not much shadow that is happening within the pan, and here you have some wind, but here wind will be going like something like this. It will not reach your water surface, so the vapor transport is affected. So these are all some of the factors why we need a,
Another factor is the size.
yeah, you can say the size also, because a pan has a limited size and water body is very big.
Yeah.
And the storage heat storage capacity of the water body is much higher than your pan. So these are all some of the factors, and that's why we are using the pan coefficient. So your evaporation from the lake is equal to 0.8 into 49. So that will be equal to 32 mm. Not 32 mm. 39.2. So next we need to determine the volume. How much amount of volume is lost. So this is a very important factor. This comes into play during the management of the water resources. So volume lost by evaporation. So you have volume is equal to, so you have the surface area of the lake is already given. Multiplied by your evaporation of lake. So volume is equal to 750 hectares to meter square is 10 power 4 into 39.2 into 10 power minus 3. So this will be in meter cube, and we are dividing it by 10 power 6 to convert to million meter cube. So that will be around 0.294 million meter cube. So this is the standard unit in which we represent. Volume is represented in million meter cube. So this is how you compute the pan evaporation and volume of water that is lost from the lake. So the next question is related to reference crop evapotranspiration using the Penman-Montet equation. So this is a lengthy question. Just see this question. So this has all the atmospheric variables calculation also. This will be related to your module 2 and 3, and you have evaporation rate and reference crop evapotranspiration. So the question is, on July 10th, the weather reported at a town in Madhya Pradesh, latitude is approximately 18 degrees north, is given. So your maximum temperature is 20.5 degrees centigrade, your minimum temperature is 16 degrees centigrade, Relative humidity maximum is 74, minimum is 53. Atmospheric pressure is given. Albedo is given. ASBS or constants, we'll come to that later. Actual bright sunshine hours is given. CP is given, specific heat capacity constant. Your elevation of the place is 26 meters. Stephen Boltzmann constant is given. Now we need to calculate this many parameters: saturation vapor pressure, actual vapor pressure, then vapor pressure deficit, gradient of the saturation vapor pressure, specific humidity, air density, latent heat of vaporization, psychrometric constant, net radiation. So we will be using that constant AS and BS in this particular calculation. In addition, it's given density of the water is 998 kg per meter cube. Roughness height is 0.7 centimeters. This is your Z1 for aerodynamic method calculation, and wind velocity is given in kilometers per hour. We need to convert to meter per second. Then we need to calculate the energy balance method, neglecting the sensible heat and the ground heat flux. Aerodynamic method, Kármán's constant is given as 0.41. Then we need to compute the evaporation rate using the combined aerodynamic and energy balance method. So the final part of the question is estimate the reference crop evapotranspiration. So this reference crop evapotranspiration, we will be assuming that the plants that grow is usually well watered, it is healthy, and it has the ideal conditions to grow, and the amount of water that is required for its growth is not limiting. So it is basically a very healthy condition, very ideal condition. It is not the actual condition. So that is the reference crop evapotranspiration. So we'll be using the Monteith-Penman equation to assume to compute this particular value. And here it is given that ground heat flux can be insignificant. So we can basically neglect the G term from this equation. So this is an empirical equation that has been derived. So if you substitute the values in this particular units, you will get your evapotranspiration in mm per day. So no need to remember very big equations. These are all some methods which you will be using. No need to remember all this. So we'll go to the question. So the first part is the saturation vapor pressure. So ES corresponding to temperature maximum, the same equation which you are familiar, divided by so this will give you in saturation vapor pressure in kilopascals. So again ES corresponding to temperature minimum, this is 1.819 kP. So here we'll be using average saturation vapor pressure because we are going to find out all the evaporation rate and evapotranspiration for the mean temperature. So I'm going to compute the ESAT. I'm just going to average these two values. So this will be 2.1155 kilopascals. So this is the value that we'll be using throughout the other calculations. Next is actual vapor pressure. So this is nothing but your EA. So in the computation of EA, so EA is related to your relative humidity, and this relative humidity has a significant effect on the quantity of your EA. So what we will be doing is, we cannot simply average like how we average the saturation vapor pressure. So we'll be using a weighted average. So that is like ES at T max. This is related to your relative humidity minimum. As the temperature increases, your relative humidity little bit decreases. So we are multiplying with the relative humidity minimum, and ES at T minimum multiplied with relative humidity at the maximum temperature whole divided by 2. So we are doing some kind of a weighted average here. .53 plus 1.819 into 0.74 whole divided by 2. So your EA is 1.3122 kilopascals. So next we need to calculate vapor pressure deficit. So vapor pressure deficit, I'll just put a delta E. This is nothing but your difference between your saturation vapor pressure and your actual vapor pressure. So delta E is equal to 2.1145 minus 1.3122. That is 0.8033 kilopascals. This is the deficit. So next parameter is calculation of vapor pressure gradient. So this is delta 4098 into ES at T mean divided by so T mean is 20.5 plus 16 by 2, 18.25 degrees centigrade. So here you need to note that if you calculate the saturation vapor pressure using T mean, it will be a completely different value than the saturation vapor pressure if you do it by averaging. So these are the just two small distinct things which you need to note down. So I'm going to calculate. This is the same expression. So this will give me 0.1316 kilopascals per degree centigrade. So next parameter is your specific humidity. So your specific humidity is 0.622 into E by P, 0.622 into 1.3122. We just calculated in the previous step, and atmospheric pressure is 100.5. QV is equal to 8.121 into 10 power minus 3 kg of water per kg of moist air. This is the unit of specific humidity. Next parameter is air density. So rho A is equal to P divided by Ra into T mean. This is in degree, this is in Kelvin. So in the first module you would have learned that your air, the gas constant for air is given by gas constant of your dry air plus 0.608 QB. But we would have approximated this to be RD itself in module 1 or 2. But here we'll be taking little bit accurate. So Ra is equal to 287 is the value plus 0.608 into specific humidity we have calculated as 8.121 into 10 power minus 3. So it will not make much difference. So you can see the value, like how much it is increasing. (288.417 joule per kg per Kelvin). So it's not much difference. It's only about 1 point some difference only. So now we can calculate the density of the air. 100.5 into 10 power 3 divided by 288.417 into mean temperature is 18.25 plus 273 converting to Kelvin. So density of air is 1.196 kg per meter cube. So next parameter is latent heat of vaporization. So here LV is equal to 2.501 into 10 to the power of 6 minus 2370 into mean temperature. (2.4577 into 10 to the power of 6 joule per kg). So we have calculated this. Next parameter is the psychrometric constant. So which is represented by gamma. In the previous question this was given directly. So your specific heat capacity into pressure divided by 0.622 into latent heat of vaporization. So gamma is equal to, this is a constant given in the question, into pressure is 100.5 into 10 to the power of 3 divided by 0.622 into latent heat we just computed now, 4577 into 10 to the power of 6. So this gamma is in 66.07 pascals per degree centigrade. So next is your net radiation. So while solving the first question I told how to compute the net radiation. So we have now here it's a little bit different. RNS minus RNL. So RNS is the net shortwave radiation. RNL is the net long wave radiation. So in first question, this net short wave radiation and net long wave radiation was directly given to us. But in this question, if you see, we have been given with the latitude of the place, then we are given month. So the latitude is 18 degree north and date is 10th July. So why have they given this information? So if you see, the radiation that is coming from the sun is not uniform throughout the globe. So it varies with the latitude. So the amount of radiation is highest near the equator and it is very less near the poles. That's why they have given this latitude information. And depending on the duration of the day, the amount of depending on the month, the amount of solar, that is the amount of sunlight during the amount of total sunlight for a particular month also varies. So in winter the amount of sunlight that you receive will be less, in summer it will be more. You'll have sun up to 6 o'clock or 7 o'clock, something like that. But in winter your sun may set by 5 o'clock itself. That is, it's not setting at 5 o'clock, but you won't get your radiation. So depending on the month and the latitude, we have two tables from which we will get some information. So it is called as the FAO table for extraterrestrial radiation. So if you see, in the middle you have been given the latitude information, and you have given northern hemisphere and right hand side is southern hemisphere. So we are in the northern hemisphere, so we'll see only that. And if you see the unit, it is in megajoule per meter square per day. So this is nothing but your radiation that is coming from the sunlight. So if I go down, I can see 18 degree north, and if I go to July, this is August, yeah, July, it is 38.9. So that is the amount of radiation that is coming from the sun. So if you see the next table, this is the table for maximum sunshine hours. So here also we have the latitude, and for each month we have how much is the maximum possible sunlight. So for 18 degree north and in the month of July, you will have a value of 13 hours. So these two information we will get from these two tables and we'll be using in our calculation. So we saw the net radiation. So this is extra terrestrial radiation. This is 38.9 megajoule per meter square per day, and we have maximum possible sunshine hours. Capital N is 13 hours. So these two information we got. So first we will see how to compute the net shortwave radiation. So that is our first parameter. So your net shortwave radiation, RNS, is given by the expression Rs into 1 minus alpha. Alpha is albedo. So what is albedo? Some amount of sunlight is coming and it falls on the surface, and a part of this incoming radiation is reflected back directly. So that is because of the albedo. So all the surface has some albedo, and snow has the highest albedo. It will be close to 1 for snow. For water body, your albedo will be close to 0 because it absorbs everything. And so what is RS in this? RS is shortwave radiation received accounting for cloud cover. So RS as a expression. So RS is equal to RA into AS plus BS into small n by capital N. So you can see where we are using the information which we got from the table. So small n is given in the question to be 10 hours. This is the actual amount of sunlight, actual sunshine hours. Denominator is the maximum possible. And AS and BS they are called as Armstrong constants. It's a constant. This is 38.9 into AS and BS is given in the question 0.25 plus 0.5 into 10 by 30. So we'll get your RS as 24.686 megajoules per meter square per day. So we got RS, so we can compute RNS now. So your RNS is equal to 24.686 into 1 minus albedo. Albedo in the question is given as 0.1. So your RNS is 22.218 megajoules per meter square per day. So this is what we wrote in the first question as SW in minus SW out. It was given directly to us. SW out was already calculated. SW in was also directly calculated, but here we are calculating. That's the only difference. So next parameter is the long wave radiation. Net so this is represented by RNL. It's a bit lengthy expression, you would have seen in the lecture also. Sigma is the Stefan Boltzmann constant. Temperature max to the power 4, temperature minimum to the power 4 divided by 2 multiplied by 0.34 minus 0.14 into square root of your actual vapor pressure multiplied by 1.35 into RS divided by RS naught divided by 0.35. So this is the expression. So in this, your temperature is in Kelvin. So rest of the things are fine. So here we have got one more new term. What is this RS naught? So RS naught is the short wave radiation received for clear sky. RS is short wave radiation received account for cloud cover. So RS we have already calculated, but RS naught we have not calculated. RS naught is given by the expression AS plus BS into RA. This is the expression. So AS plus BS is 0.25 plus 0.75 into RA is 38.9. So your RS naught is 29.175 megajoule per meter square per day. So now we have all the terms which we calculated, which is necessary to calculate. So I'm just going to substitute in that big expression. RNL is equal to 4.903 into 10 power minus 9. This is the Stephen Boltzmann constant. And 293.5 power 4 maximum temperature, 289 power 4 minimum temperature, multiplied by 0.34 minus 0.14 into square root of your actual level pressure, 1.3122. Multiplied by 1.35 into your RS is 24.686, which we calculated previously, and your RS naught is 29.175 minus 0.35. So this is a big expression. So if we calculate this, your net long wave radiation that is emitted from the surface of the earth is 5.022 megajoule per meter square per day. So net radiation. So this RNL only is long wave in minus long wave out, which we saw in the first question. So your net radiation now is RNS minus RNL. Net radiation is 22.218 minus 5.022. Your net radiation is equal to 17.196 megajoule per meter square per day. So this is how we get the expression for net radiation. So we need it in terms of watt per meter square. So I'm just converting it, 1.196 into megajoule to joule divided by 86400. So joule per second is watt, 199.03 watt per meter square. Okay, so we are just computing it and keeping it, we'll be using it. So now coming to the next part of the question. So we have computed, I think this is J, I guess. So I, next is J. So now we need to estimate evaporation by energy balance method. So your evaporation by energy balance method, ER is given by Rn divided by, so we are neglecting the sensible heat as well as the ground heat flux. So divided by rho W. So ER is equal to 199.03 into 10 to the power of 3 into 86400 divided by latent heat we calculated in the first question itself, 4577 into 10 power 6. Density of the water is given as 998. So ER is simply 7.011 mm per day. So next we need to estimate by aerodynamic method. So this is K subdivision. So EA is equal to 0.622 K square rho A ES minus EA divided by rho W into P into U2 divided by ln of Z2 by Z1 the whole square. So we have computed all the parameters. 0.622 into 0.41 square into density of the air is 1.196 into 2.1155 is saturation vapor pressure, 1.3122 is the actual vapor pressure into 10 to the power of 3 into velocity is given in terms of kilometer per hour, but we need in terms of meter per second into 1000 by 3600. We are converting to meter per second. This whole expression divided by 998 is the density of the water, 100.5 into 10 power 3 is the atmospheric pressure into natural log of. So we are measuring the wind velocity at 2 meters above the ground, and Z1 roughness height is given as 0.7 centimeters in this question. Whole square. So if we evaluate, so again we need to convert this. So if we do that, 3.497 into 10 to the power of minus 8, this is in meter per second, into 10 power 3 into 86400. EA will be 3.022 mm per day. So next is the combined method. So this is also a familiar expression. E is equal to delta by delta plus gamma into energy balance method evaporation, gamma by gamma plus delta aerodynamic methods evaporation. So here E is equal to 131.6 divided by 131.6 plus 66.07 into 7.011 plus 66.07 divided by 66.07 plus 131.6 into 3.022. So this is equal to 5.678 mm per day. So we have computed this also. So the last part of the question is estimation of the reference crop evapotranspiration. So all the above things are just evaporation. So this is evapotranspiration. So your Penman-Monteith equation is Et naught is equal to, it was given in the question, I am just substituting the expression directly, 0.408 into your delta 0.1316, this is in kilopascals per degree centigrade, into your net radiation in terms of megajoule per meter square per day plus 66.07 into 10 power minus 3. This is psychometric constant in kilopascals per day multiplied by 900 divided by your temperature mean, that is 18.25 plus 273, we are converting to Kelvin, into your wind velocity in meter per second, 1000 by 3600, again multiplied by ES minus EA, that is your vapor pressure, saturation, vapor pressure deficit, you can say it as vapor pressure deficit, which we calculated, delta E, whole divided by 0.1316, this is your vapor pressure gradient, delta plus gamma, 66.07 into 10 to the power of minus 3 psychometric constant plus 0.34 into 4 into 1000 by your wind velocity in meter per second. So if you evaluate this expression, you will get your reference crop evapotranspiration as 4.966 mm per day. So when healthy grass under ideal conditions with sufficient amount of moisture is exposed to the solar radiation which we calculated in the previous steps, and temperature and climatic conditions in the previous step as given in the question, so it can give a evapotranspiration of 4.966 mm per day. So but this is under ideal condition, but in the next question we will see for a given crop and a crop coefficient how to estimate the evapotranspiration. So each crop will have a different crop coefficient and different evapotranspiration rates. So that's why we need the Kc, that is the crop coefficient. So this is the final question for the day. So here we will be determine the crop coefficient at different days. So as the crop grows, you will have a different crop coefficient. So from the sowing date to the harvesting date. So here you have been given a table. So this is the crop growth stage, number of days, and your crop coefficient. So first 25 days it is 0.15. From the 26th day until the 50th day it is around 0.15 to 1.19, and it is varying linearly between this date. And from the 51st day until the 80th day your crop coefficient is constant, so your plant is growing, and towards the end, the last 20 days, again it is dropping because the growth of the plant is almost completed and it's ready to harvest. Your crop coefficient again decreases. Now we need to compute crop evapotranspiration. This is crop evapotranspiration on the different days, given that reference crop evapotranspiration they have already given in the question. So these are the reference crop evapotranspiration at 10 days, 20 days, 30 days, up to the 100th day in mm per day. So now we can plot how this crop coefficient varies. So this is your x and y axis. So this will be your crop coefficient and this will be number of days. So it varies something like this. So first 20 days it will be constant, then again it increases, it is plant is growing, and the plant has reached a certain amount of growth, and just before the harvest it again decreases. So this is the kind of variation. So here it is 0.15, here it is 1.19, and here it is 0.35. 0.35. So the different stages, let's say initial, development, mid-season, late season. Okay. So if I draw the corresponding stages here, so this is your first 20 days, then next 25 days, this is your 80th day, and this is your 100th day. So it varies something like this. So here you will be sowing your seeds, and towards the end it will start to grow. Then in this stage it will grow little bigger. Then here it will grow even bigger, it will mature, and let's say it gives you the grain. So this is your harvest product, and later you have harvested it and something is remaining. So this is how it varies. Now they have given the crop coefficient is something varying like this. Now we need to determine at different stages. So we can make use of the linear interpolation and we can compute the at the required dates. So they have asked for crop coefficient at 20th day. 20th day it is 0.15 only. At the 40th day. So 40th day will come somewhere in between here. So that we can compute by linear interpolation. So 15 by, this is just linear interpolation. So 1.19 into so this will be equal to 0.774. Then your 70th day, 70 will come somewhere here and it is constant 1.19. Then your 95th day, again linear interpolation. It is 15 by 20 into this is around 0.56. So your 95th day comes somewhere here. So your 20th day is here. So these are the 4 points they have asked the crop coefficient and we have calculated the crop coefficient. Part B of the question, we need to compute the crop evapotranspiration and they have given the reference ET. So the expression is ETC, this is your crop evapotranspiration, is equal to ET naught, this is your reference evapotranspiration multiplied by your crop coefficient. It is a very simple expression, just similar to your lake evaporation and pan evaporation. So they have asked for every 10 days, what is the every 10th day, what is ETC. So I am just going to write it, KC ET naught and ETC. So similar to the first question, we need to compute the Kc. So wherever it is constant, we can write directly, and wherever it is not constant, we can do the linear interpolation. So this is 0.15, again 0.15, this is 0.358, 0.774, 1.19, 1.19, 1.19, 80th day is also 1.19. 90th day again it decreases, and your 100th day is 0.35, that is the last value. And ET naught is given in the question, 3, 3.4, 4, 4.2, 4.5, 5.1, 5.6, 6, 5.5 and 5.2. So just multiply these two, you will get the ETC. So you can see how the crop also behaves. So from the seeding point till the harvesting, your ETC slowly increases, it reaches a maximum value and then again it drops down just before harvesting season. So this is how we compute the ETC. So this brings us to the end of the session. If you have any doubts, you can ask.
Yeah.
Yeah.
Wonderful presentation, and it's very knowledgeable, and you given the input and knowledge. And thank you so much.
Yeah. Yeah. Thank you. So this materials will be shared.
Yes, sir. In my on my email ID.
Not in the email ID. So I will just a minute. I will just share the link. So this video will be uploaded in the YouTube channel.
Okay, sir. Okay.
And the presentation, I think it will be shared by the NPTEL coordinators
Okay.
as a drive link, I believe. I think so. We are all uploading it in the Google Drive, so I think
Okay,
that
sir.
drive link will be made available.
Okay. Thank you.
Yeah.
Thank you. Thank you so much.
Yeah. Thank you.